Well, good afternoon, ladies and gentlemen. We're going to continue on with entropy and look at a particular kind of process that will crop up over and over and over again now that we have a little bit further grasp on entropy over the last several days. We're going to look at what's called isentropic processes. Isentropic processes refer to constant entropy properties, or of course, no change in entropy over the process. So remember, we had isobaric, isothermal, isochoric, adiabatic, isentropic, so constant entropy or no change in entropy process. Delta S is equal to 0 or constant over the process. So we're going to focus on isentropic processes involving ideal gases. That's mainly the application that you're going to see this sort of thing this semester. So we're going to look at we're going to look at property relationships and how they reduce in the case of isentropic processes. We're going to look at the property relationship, see how they reduce for isentropic processes for constant specific heat and variable specific heat. And then we'll do an example today, okay? So we're going to derive some isentropic property relationships, how temperature, pressure, specific volume, how they're all related when the process is isentropic, entropy doesn't change or is constant, okay? So let's get started here. So isentropic processes. Isentropic processes. So on a TS diagram, so here's temperature, maybe there's some isobars in here. So here's pressure. So isentropic processes refer to a movement up or down vertically along a line of constant entropy. So an example would be some sort of heating, some sort of compression process going from some pressure to another pressure. We're raising the temperature of some sort of a gas or something by compressing it and increasing the pressure going from state 1 to state 2. So this would be a piston cylinder device containing some kind of a gas, state 1, and a temperature T1 and P1. And then let's say it's adiabatic process here. We wrap some insulation around it. And let's compress the piston down, raising the pressure, raising the temperature. So the piston goes downwards. So we have some sort of an isentropic compression to a temperature T2 and P2. All right, so that might be what's going on in this TS diagram here. Some sort of an isentropic compression process of a gas. Pressure goes up. So here's P1 and here's P2, okay? So that's an example. Now, where do isentropic processes tend to crop up? Well, let's write the entropy balance for a closed system. So here we have a closed system here, going from state 1 to state 2. Okay, so we have S1 and S2. So if we write the entropy balance on our system, it's a closed system, we can see that here. We see delta S from 1 to 2 is equal to the sum of the integral of del Q over the interaction temperature plus entropy generated due to irreversibility over the process, okay? Now, if this particular process involves no heat transfer, so let's say adiabatic, it's adiabatic, so that means the heat transfer term goes to 0. And if it is reversible, If it's reversible, then S gen is equal to 0. 0 reversible, 0 adiabatic. Okay. Then, of course, we have delta S equaling 0, or a isentropic process. Delta S 1 to 2 equals 0. Isentropic. So if we have reversible adiabatic processes going on for a closed system, that usually implies that it is a isentropic process. But of course, you need to write the entropy balance and see whether it is an isentropic process. Want to write that out for yourself to justify, okay? So when we have reversible adiabatic processes for a closed system, usually that implies an isentropic process, or delta S is equal to 0. Let's develop some relationships between pressure, temperature, or volume, or specific volume for, let's say, an ideal gas under the constraint of an isentropic process. So let's get an equation that relates, let's say, temperature and pressure, or temperature and volume, or specific volume, as for an isentropic process. So the isentropic property relationships, ideal gas, so IGB, ideal gas behavior, isentropic prop relationships. And we're going to look at constant specific heats first. Constant CP and CV, constant specific heats. Okay, so we previously had two equations that were valid for an overall process, ideal gas behavior, constant specific heats. As you recall, we had two equations. We had delta S, or the change in specific entropy from state 1 to state 2, equal, and I had two expressions. I had CP ln T2 over T1 plus R ln P2 over P1. Okay, that was one expression. We developed this a lecture or two ago. I think it was 2 lectures ago. And then we had, so this was based on enthalpy. That's why it's got a CP in there. And then we had CV ln T2 over T1 minus R ln V2 over V1. This can be specific volume or volume, doesn't matter. The masses cancel out in the fraction, okay? So if delta S is equal to 0, so if this guy is equal to 0 for an isentropic process, then that implies, so let's look at the first equation here. That implies CP ln T2 over T1 equals minus R ln P2 over P1. Okay? Now I'm going to divide both sides of the equation by the specific heat, CP. So I get ln T2 over T1 equals R over CP ln P2 over P1. Okay? Now CP, well, tell you what, R, for an ideal gas, what's the relationship between specific heats and the gas constant R? So recall, for IGB, CP minus CV is equal to R. Or if you like, Cp is equal to Cv plus R. We had that result several weeks ago, okay? Long time ago. So I'm going to make a substitution for R here. So we get Cp minus Cv over Cp. That's what that ratio is, R over Cp. And then that gives me 1 minus Cv over Cp. 1 minus Cp over Cv. Now, Cp over Cv, I only mentioned this one time. There's a quantity K. K is referred to as the ratio Cp over Cv. We talked about this a while back, but let me remind you, we have a symbol, a quantity that gives you the ratio of specific heats. Let me show you here. Let's go to the ideal gas tables, and I'll remind you where K is shown. So here we have specific heats. All right, table B10, ideal gas specific heats for various gases. Temperature, Cp, Cv, the ratio. Here's K. K for various gases as a function of temperature. Why? Because Cp and Cv vary with temperature. So K, which is the ratio of Cp over Cv, varies with temperature. I should have one for air. Here's air. Oops. I guess air is up here. Yeah, so here's air. So if you need specific, if you need the ratio of Cp over Cv to do a calculation, then you can look it up in table B10. So K is a function of temperature, just like Cp and Cv are functions of temperature. After all, K is the ratio of Cp over Cv. So this quantity here, Cv over Cp, is 1 over K. So this whole thing is 1 minus 1 over K. All right? Okay, so let me write the last. So we got 1 minus 1 over K, natural log P2 over P1. Okay? Now I'm going to take this quantity in parentheses here and stick it inside the natural log, so multiplication becomes exponentiation. So this implies ln T2 over T1 equals ln P2 over P1, and then I've got in the exponent 1 minus 1 over K. Okay, so that's inside the natural log. Let's raise everything to the nth power and get rid of the natural log. And I get T2 over T1 is equal to P2 over P1, 1 minus 1 over K. All right? So this is our first isentropic property relationship. It relates pressure and temperature at some initial and final state for an isentropic process. So let me get rid of this here, and I'm going to write right next to this equation. This implies T2 over T1 equals P2 over P1, 1 minus 1 over K, okay? You can do the same thing with the second equation involving pressure, involving specific volume. So you can go through the same derivation and you get a similar equation. I don't have them memorized. I always have to look them up. Let's see, we get the ratio of temperatures, T2 over T1 is equal to the ratio of the final to the initial specific volume. And then in the exponent, we have, let's see here, 1 minus k, 1 minus k, 1 minus k, all right? By the way, this first equation right here, sometimes the exponent is written a little bit differently. You can get everything with the same common denominator. I could multiply the 1 by k over k. So then that means the second and the first term are same denominator. And so I'll have a k minus 1 over k. You can write it like that as well. It's the same quantity, okay? So sometimes this is written as k minus 1 over k, all right? In fact, I think I have that in the notes. It's the same thing, all right? It's the same thing. Okay, so we have two isentropic property relationships relating temperature, pressure, and volume for a constant entropy process. So let me rewrite these here. T2 over T1 is equal to P2 over P1, 1 minus 1 over K, and that's the first one. And then I have T2 over T1 is equal to specific volume at state 2 over specific volume at state 1 minus K. So these are the isentropic property relationships valid for IGB, constant specific heats, and constant entropy. So IGB, constant CP, CV, and therefore K. K is the ratio of specific heats. Usually in these problems, you're told to evaluate K at some temperature. Just like in past problems, you were told to evaluate specific heat at some temperature, okay? So IGB, constant specific heat, delta S from 1 to 2 is 0. In other words, isentropic process. So there's your isentropic property. Oh, sorry about that. Let's just go over this again. So a little bit of algebra. On the first property relationship, delta S is equal to 0. And we arrive at T2 over T1 is equal to P2 over P1, 1 minus K over 1 minus 1 over K. Luckily, I think you can see a small version of the screen while I'm working. Sorry about that. And then we did the same thing with the second equation on a property relationship. We had T2 over T1, V2 over V1 to the 1 minus K power, okay? So these are both valid for constant specific heat, delta S equals 0, isentropic process, IGB, okay? Now what's another way to relate properties, pressures, volumes for an isentropic processes? How do we do that? Well, how do we do that for variable specific heat? So how about variable specific heat? What are the relationships between temperature, pressure, and volume for a constant entropy or no change in entropy process if we have variable specific heats? So isentropic process, variable, isentropic property relationships. For variable specific heat. And again, this is for ideal gas behavior. So make sure IGB, ideal gas behavior, okay? Well, let's take a step back here And recall, we had an equation giving delta S for variable specific heats involving those S naught quantities. Remember, it was S naught evaluated at T2 minus S naught evaluated at T1. And then I had a plus R ln P2 over P1. Okay? So if it's isentropic, delta S is equal to 0, all right? So isentropic, so delta S is equal to 0. So in theory, if you have, let's say, an initial temperature, and you have the two pressures, the initial and the final pressure, you can look S naught at T1 up in a table. You can calculate this quantity, and therefore you could calculate S naught at T2. And then you could back out the temperature using a IGB table to get T2. So you could use this equation. You could use this equation with the left-hand side. So I could do the following. I could say S naught T2 is equal to S naught T1. And then I have minus R ln P2 over P1. I could do that. Okay? I could do that. And I could, if I knew T1, I could get S naught at T1. And I know the pressures, so I can calculate this term. So I can get S naught at T2. Okay, I could do this. I could do this. All right? Now, there's an easier way to do this, a much easier way. And it utilizes reduced pressure. Remember reduced pressure? We were talking about the ideal gas law about a month ago. We introduced reduced pressures and reduced volumes and reduced temperatures. Well, there's a quick and easy way that these properties, pressures and temperatures, can be related for an isentropic process using reduced pressure. So you could do this. This is okay. I'll put a question mark here. Not very easy to do. It's laborious. We're going to do something else instead. We're going to say, for isentropic process, the reduced pressure PR2 over PR1 is equal to P2 over P1. Okay, where these reduced pressures, these are not the same reduced pressures, they're not numerically the same reduced pressures that we are used to with ideal gases, where we divide pressure by the critical temperature pressure. It's not the same thing. It's a rescaled pressure. So these reduced pressures here, these are available in tables. Tables, IGB tables, and they're a function of temperature. Function of temperature. So for example, so let's see how this would work. How would we use this expression? Let's say you are given Let's say you're given that it's an isentropic process. You're given T1, you're given P1, and you're given P2. And you want to find temperature T2. That's what you want to find. Well, how would this work? So, procedure. You would first look up reduced pressure PR evaluated at temperature T1 from an IGB table. Let me show you here what this might look like. So here we have IGB tables for air, HU S naught, function of temperature, reduced pressure, PR, as a function of temperature. So if you had T1, you would find PR1 by finding the temperature and then going over horizontally to get PR. Maybe you have to interpolate, who knows? Who knows? Maybe you have to interpolate, who knows? So look up PR evaluated at T1. Then you would calculate PR2 is equal to, I would use this equation, PR1 times the pressure ratio, P2 over P1. I've got the reduced pressure temperature T1. I have the pressures to get the pressure ratio. Therefore, I have PR2. Look up temperature evaluated at P, so T2. To get T2, find the final temperature, which is equal to the temperature evaluated at PR2. And you would look this up from a table. So once you have PR2, you would go to your table. So let's say you knew what PR2 was at state 2. You would find it and then go over and get the final temperature at state 2. So this procedure allows you to calculate temperature changes as a function of pressure using reduced pressures, and this incorporates variable specific heat. By the way, there's another way to do this. Let's say you were comparing, let's say you had temperatures and volumes instead of temperatures and pressures. You can relate, you can relate volumes to reduced volumes, which are a function of temperature. So also V reduced 2 over V reduced 1 is equal to V2 over V1, where these are reduced volumes. Reduced, actually they're specific volume, and they're from tables. Okay, you could do the same procedure here if you had the volume ratio, you had an initial temperature, and instead you would be looking up reduced volumes instead of reduced pressures. Okay, so let's stop here for, maybe before we do, I want to point out, this is getting to be a lot of equations. And as I mentioned last time, I provided a nice table for you to kind of condense all this stuff you have to remember. Let's find it again. Let's see here. It's in tables, chapter 6. I think it's table 6.2. Here we go. Right before open system entropy balance, which we're going to go to next time. Page 124 in the notes. You'll see it right here on the bottom. I have isentropic processes overall. So here we have equations for variable specific heat, constant specific heat property relationships. And so here's this PR and VR equations here, okay? PR and VR equations. So just reminds you, condense what we've done today. And remember, these are the property relationships for entropy, differential overall per unit mass, et cetera, et cetera. These are all provided for constant and variable specific heat, IGB, et cetera, in table 6.2. So this is I hope, a fairly helpful table that would condense a lot of the information. There's a lot of information here, so I think you need this table. We're going to get on and just do an example here in a moment.